So I'm going to give you a quick idea of what's involved in Chapter 8, so you have an idea of the overall sense of the chapter itself. So Chapter 8 starts with potential energy, which we've already talked about. It then talks about conservation of energy. We talk about mechanical energy versus overall energy, and we talk about work done by an external force. So Chapter 8 is very much like Chapter 7 was with energy again. Okay, with energy. Now, something I want to point out is that I use PE for potential energy. Your text and AP exam uses capital U. So I'm going to try to adopt that nature so you guys can see it a bit better. Okay, and U is equal to mgy. Okay, and this is gravitational potential energy. Gravitational potential energy. And then the other U we already talked about, which was energy stored in a spring. Okay, energy stored in the spring. And I called that elastic energy always. Okay, if you want to call it UE or just U, that's fine as well. All right, and this last point, let's take a look at this theory here. This last part is very unique because we've talked about the change in kinetic energy and work. This next theory or this idea is that the change in potential energy is equal to the negative work done. Okay, is equal to the negative work done in this problem. And if you think about this, if I were to think about an object moving from here up to here, and I think about the work done from here to here, if I were to do that, I might have a force being applied by a cable lifting it up a certain distance. But we said a moment ago that if you're lifting an object up, what kind of work is gravity doing? Gravity is doing negative work because it's pulling down. So that's what we're seeing right here. That the potential energy gained by something is equal to the negative work done by gravity. Okay, so that's the concept of the theory behind this in this chapter. So that's really section 8.1. 8.1. Now, 8.1 goes into a little more detail, and I'll explain the problem that's going to matter to you guys for the exam about this scenario. You've got a person sitting here at the top of something, and it takes that route, or that route to end at the bottom. So here's the first object right there, and it ends at the very bottom. And the theory behind this is taking which path will cause the object to gain or lose or more potential energy or do more work. And the idea behind it is that really, what are you doing? You're changing height by the same amount. So no matter which path you take in this problem, you really do gain the exact same amount of energy. And this concept is called conservative forces is what it is. So in this case, we'd say that gravity is a conservative force. Which implies that the path taken does not matter. So if you start with a certain amount of potential energy, and let's say that potential energy is 36 joules, and you end with a potential energy of 0 joules, whether you took the top path, the middle path, or the bottom path, the work done is still going to be the same value. The change in kinetic energy is still going to be the same value. Now, if I look at this problem, right, and I think about the final minus the kinetic, final minus the initial for potential energy in this problem, we want to recognize here that we're looking at 0 minus 36. Right? So if I say final minus initial equals the negative work done, this is really going to be 0 minus 36. And we look at this, we see, negative 36 joules of work is done, and that equals the negative work. So what kind of work does gravity do in this problem? Gravity does positive work. If you want to put a G for work done by gravity for all of these, you can. Okay. Gravity does positive work here because which way is the object moving? It's It's moving down. It's moving down. That's where the negative sign comes from in this theory right here. Now, personally, I think this gets very confusing to remember the negative, the double negative. So I'm going to show you guys a way that I attacked these problems when I was in your seat in high school. And I think this method is a lot easier. And the idea really is just go right to conservation of energy every time. Go right to conservation of energy. And the theory behind conservation of mechanical energy we'll talk about first is the following. The conservation of mechanical energy tells me that the energy in the system initially will equal the energy in the system at any other point in time. You can say initial and final. I haven't been using F for final, but the book suddenly is using F here, so I'm kind of using the F as a subscript. All this means is that at any moment, the total energy in the system is conserved. So let's look at that same example here. Okay, here's the object in the beginning. Here's the object at the end. In the beginning, let's say it's got energy of 15 joules in potential and no kinetic. Okay, 0 in kinetic and 15 in potential. That's a capital U, not a V. I hate using U, sorry. It's a capital U there. If we want to figure out the amount of energy at any other given moment, all we need to know is how much of one of the energies we have. So if I tell you a couple of meters in that we have 3 joules of kinetic energy now, how much potential must we have? We must have 12. Because again, at any moment in time, the total mechanical energy is conserved. It has to be equal at any moment. So then we go to the next part.
This is without friction.
Correct. Mechanical energy. Friction is different. That's what we're going to talk about thermal energy when we get to that. So this is all about without friction here. So let's say the kinetic is now 5 joules. Means the potential must be 10 joules. This is not drawn to scale, obviously, height-wise. And then at the very end, we'll say that it's all kinetic, and therefore potential equals 0. Okay, you definitely did this at some point last year, whether you were in my class or the other class, because you had to have seen conservation of energy. And the concept, though, is that at any moment you sum them together and it equals a constant. It equals a constant. Okay, and again, this is mechanical energy. Mechanical energy. Okay. That's 8-1 and 8-2. Yeah, Max, go for it.
So, once it gets to the bottom, I guess this involves friction, my question. Because it wouldn't make sense that
Of course.
15 kinetic.
Totally, Max. And we're going to talk about that. So that's kind of what we're leading into right now. So the question then becomes, what if your energy in the beginning and the end don't match up? What could have caused that? And that's going to be work done by friction. So as a result, if we knew the distance traveled along this arc length, we knew D, we could find the force of friction by figuring out what the work missing was. And let me show an example of that, okay? So let's do the same kind now. And let's say in this case, the sum of energy in the beginning equals the sum of energies at the end. So this is all types of energy now. So we've got potential in the beginning, kinetic in the beginning. Now, in the beginning, actually, we're going to say, here's how I like to put it. We're just going to leave it like that. And then we're going to say the following. We're going to say we have potential at the end, kinetic at the end, but we also have work done by friction. Last year I used to call this Q loss. If you remember from last year, Q loss was the energy done. Your book doesn't use that phrase. Your book, I think, if I'm correct, just uses W for work done when they talk about it. If they even do they do it? Let's see. They call it E thermal. So I'm going to call it E thermal. And that's exactly what Max is asking about. What if we lose energy to friction along the way? Maybe we have 15 joules to start, and then at the end we've got 12 joules plus the energy that's left over. It means that we lost 3 joules of energy to friction. And if we know that this turns out to be 3 joules, well, that's the work done. All right, that's really the work done. So this becomes 3 joules equals the force of friction times the distance traveled. And then we could solve for either one of these two variables. Either we solve for friction or we solve for the distance traveled along the arc length. We're going to get into this one more next class, okay? So chapter 7, practice, get started on the homework board, please. I will try again, as I've done in the past, to send you also AP old problems for multiple choice or free response. The multiple choice that you guys do on the slideshow ones are pretty much AP level problems. The free response, though, I like to give you old example problems. So I'm going to search for more of those, especially now that you've covered a lot more. Now that you've covered kinematics, we're going to do something that involve energy and kinematics together. Okay?